Hi, this is Barrett Givens. In this video, we're going to introduce a new concept of a property of topological spaces called Hausdorff, and then we'll prove a theorem that tells us one reason why topological spaces being Hausdorff are sort of extra nice, okay? Why being Hausdorff is a desirable property. All right, so a topological space X is Hausdorff if and only if. The idea of being Hausdorff is that anytime you take 2 points in the set, there are open sets that kind of separate the 2 points. Sometimes Hausdorff is called a separation axiom. Okay, so it's about separating points. So it's Hausdorff if and only if for all little a and little b in X, there exist open sets U and V such that A is in U, B is in V, and U intersect V is empty. Okay, so let's draw a little Venn diagram to kind of demonstrate what this looks like. So here's my space X. I take 2 points, A and B, and it says that whenever I have this situation, whenever I have a situation that looks like what I have here, there exists, so I can find open sets U and V that don't overlap at all, and A is in U and B is in V. Okay? So let's go through a couple of examples, and then I'm going to show you the theorem that is part of why we really like spaces being Hausdorff. And a lot of the spaces that we consider are Hausdorff, but not all of them. So as my first example, let's let X be R2 with the standard topology. So that means the topology defined by having a basis of open balls. So let's look at my space X. I often picture it as with horizontal and vertical axes. And let's take 2 points. Let's say 1 point, I'll call it A, which will be A1, A2. And then the other point I'll call B, which will be B1, B2. And I want to know, can I put two open sets around the points A and B, and those open sets should not overlap. And I could do any kind of open set, but it's usually easier to do a basic open set, And remember here, the basic open sets are circles. So I'm going to just try to find two circles, one centered at A and one centered at B, that don't overlap. Okay? And I mean, certainly I can just sort of draw it, but let's just algebraically think about what that would look like. I'm going to look at the distance from A to B. So let's let R equal the distance from A to B. So that's R. And I just want to make two circles whose radiuses are such that they don't overlap. So what I'll do is I'll let epsilon be R over 2. Then I'll let U be B sub A epsilon and V be B sub B epsilon. So epsilon sort of goes halfway to the point between A and B. So maybe that's halfway right there. So the ball around B looks like this, and the ball around A looks like this. Oh, it looks like they're touching. They're not supposed to overlap. Do they overlap here? Do they overlap? No, because these balls, it's open balls, which means they don't include any of the edge points. So they come extremely close to each other right here at this halfway point between A and B, but they do not touch. Okay? And clearly A is inside of U because it's the ball centered at A, and B is inside of V, and U intersect V are disjoint. All right. That means that, and you know, A and B were arbitrary here, right? I just picked two sort of like random points in the plane, and I was able to do this. And if you imagined if you had two other points, you could always do this way. And so therefore, R2 with standard topology is Hausdorff. Okay, let's do a second example. Let's consider the finite complement topology again. Suppose X has the finite complement topology, and X is infinite. So X is an infinite set and it has the finite complement topology. Let's let A and B be elements of X. So I'll maybe picture X just like as a line. I don't know what kind of a space X is. X could be anything, but just for the point of picturing it. So here I have A, here I have B. And I want to try to find two sets U and V that are both open. So if U and V are both open, then their complements are closed, okay, and their complements are finite. So if U and V are open, then their complements are finite. So like maybe you maybe could leave B out, right? Maybe you could look sort of like this. You could have just a few holes in it, but it includes everything else. And then V, I'll leave A out and it might have a few other holes, but it can have only at most finitely many holes. Okay? So U and V, they're both open, which means their complements are finite. I claim that I can't quite make U and V like avoid each other, that there's going to be some overlap in U and V because the fact that their complements are finite means U and V each include like almost everything, right? So let's formalize this. All right. Suppose U is open with A in U and V is open with B in V. So suppose I take two open sets where A is in one of the sets and B is in the other set. Then U intersect V. Let's look at what U intersect V complement looks like. U intersect V complement would equal U complement union V complement. And because U is open, U complement is finite. And because V is open, V complement is finite. So this is a union of finite sets. So there's only finitely many things in U complement and only finitely many things in V complement. Well, if I put two finite sets together, it's still finite. It doesn't magically become infinite just because there's two of them, right? Thus, U intersect V complement is finite. And that means that U intersect V can't be the empty set. It can't be the empty set because if it were the empty set, then its complement would be all of X. And we know that all of X is infinite. So U intersect V can't be the empty set. And this means that the finite complement topology is not Hausdorff. Okay. So being Hausdorff is like a really nice property. So in a way, this tells me that the finite complement topology is a little bit not so nice. Okay. It's a little bit pathological, is what we might sometimes say in mathematics. Basically, in the finite complement topology, if you're given 2 points like this, you can't get two open sets that one contains 1 point, one contains the other point, and the two sets don't touch each other. If you have two open sets that contain two different points, there has to be some overlap between those two sets. Okay. Another way of thinking about it is that open sets in the finite complement topology are like really big. Okay, they're really big. Their complements are finite, so they have to kind of like cover a lot of stuff. So when you overlap two of them, it's still really big. All right. Okay. And then finally, we have this theorem about Hausdorff spaces, Um, if a topological space is X is Hausdorff, then singleton points will be closed for every little a in capital X. So this is a nice property. Let's prove this. Proof. Suppose X is Hausdorff. Let's let F equal singleton A. I want to show that F is closed. The definition of closed is that its complement is open. So then F complement is equal to X minus singleton A. So if I think about, here's my set X, I sort of make an open circle at A. F complement is everything that's outside of that, everything but A. All right. I want to show that F complement is open. There's more than one way to show that a space is open, but I'm going to do it by showing that F complement is a neighborhood of each of its points. So I will show that F complement is a neighborhood of each of its points. So let's take a point in F complement. So let's let B be a point in F complement. I want to show that F complement is a neighborhood of B. So take that point B. I want to find an open set that contains B. I have this hypothesis that X is Hausdorff. So because X is Hausdorff, there are open sets U and V such that A is in U, B is in V, and U intersect V is empty. So let's draw those in. So I'm going to have a U around the point A and a V around the point B. Okay? Now we claim that V is a subset of F complement. Why is that? Well, we know that A is in U, so A can't be in V. A is in U, and U and V don't overlap. So A is not in V. A is not in V. And that's kind of the meaning of being an F complement. Okay. Thus, we have found B, element of V, subset of F complement, and remember that V is open. So we've made this format here where we've showed that F complement is a neighborhood of V. Sorry, F complement is a neighborhood of B. There are too many letters in this proof. F complement is a neighborhood of B. And B was arbitrary. B was arbitrary. Thus, F complement is a neighborhood of each of its points, which means F complement is open. And by definition, that means F is closed. Okay, so what did we do in this proof overall? We started by assuming that we had a Hausdorff space, and we want to show that singleton A is closed for any A in X. So we took the set singleton A, and just so that we could talk about it more easily, we named it F. Okay. And then we want to show that F is closed. To show that F is closed, we'll show that F complement is open. to show that F complement is open, we'll show that it's a neighborhood of each of its points. Well, being a neighborhood of each of its points means we need to take an arbitrary point B. We took this arbitrary point B and we used the Hausdorff property to draw sets U and V, where U is around A and V is around B, and U and V are separated from each other. They have no overlap. Because they have no overlap, that means that V is a subset of F complement. And so we get this situation here where we have, this is sort of the key fact right here. Every B that we pick, we can find an open set V where B is an element of V, which is a subset of F complement. And that means that F complement is a neighborhood of the point B. And since B was arbitrary, that means that F complement is a neighborhood of every single one of its points. No matter what point I picked, F complement would be a neighborhood of it. And we have a theorem that says that that means that F complement is open. And by the definition of closed, if F complement is open, then that means F is closed. Okay, so that's the proof of this theorem. Thank you so much for listening.